Good morning, everybody. This is a nice problem in terms of balancing algebra. We can call it algebra versus computation, I guess. Now, the computational aspect of this would be to actually try to find a, b, and c in this cubic and then raise each of them to the fifth power and then sum. So this is algebra really. What I'm showing you is algebra versus shall we call it calculation or computation. And again, it's very tempting if you just look at this for the first time, you haven't seen this type of problem. You're thinking, well, I'll just find the roots and then raise each of them to the fifth power and then take their sum. Easier said than done. Okay. So this is algebra versus computation, and I've elected to do the algebra root. Now, there's no easy path to Rome here. One thing that's super important here is to find out that these zeros appear as coefficients in the polynomial. In other words, the negative sum of the roots appears in front of x squared. Their products, the pairwise products summed, end up as the coefficient of x. And finally, the negative product of the roots appears as the constant term. So this is very, very important. And so we can write down a plus bc is equal to 0, why? Well, really, there's an x to the 0, there's a 0x squared term right here, right? Which actually makes this problem tractable. If you don't have that, I'm not sure how to do this. It's very difficult. So there is a 0x squared term right here, and the 0 you see right here is the 0 that you see right here, okay? And also, when you expand this out, the minus sign presents, right? So that's why it cancels right here. ABC is equal to 19. And you don't have to worry about the sign alterations with this piece right here. It's just the 7 that you see right here is the 7 that you see right here. Now, the part that's really hard, where I left out a ton of work, is expanding this out. You're motivated to expand this out because if you expand this out, in other words, what I'm telling you is that this expansion is equal to this next line, okay? It's equal to the next line, okay? And so, and the fact that a plus b plus c is equal to 0 is the cause of this step right here. The yellow, I did use the multinomial coefficient. I made some mistakes, so I eventually used technology to get this right. But you can use the multinomial coefficient. Actually, you can use the binomial also, but it's very, very tedious, and I didn't want to drag you through all of that. And so what I'm trying to tell you is when you expand this out, you get this statement right here. And then when you note that a plus b plus c is equal to 0 from the Vieta's result, we get this statement right here. So we have what we're looking for. We're trying to evaluate a to the fifth plus b to the fifth plus c to the fifth, and we know this much, okay? Now, something that's super, super cool that I didn't notice until I looked at it for quite a long time is we use this 3 times to change this entire piece right here. See, this entire product right here just becomes 5abc mysteriously. How did that happen? Well, notice that a plus b is negative c. Right? Isn't that cool? b plus c is negative a. And I'm just using this. C plus a is negative b. So you can see how you have 4 negative signs here. The negative sign that's already present, and then the negative sign that results from applying this result right here, a plus b plus c equals 0 3 times. So we end up with this. Now we're in fairly decent shape because we know quite a bit. You know, we know that ABC, we know what ABC is, and we know what this object is right here, you see. And so on the very next line, I make these substitutions, you guys can see. Okay, 5 times 19 is 95. And then the 7 comes into play. You can just see a straight substitution from the initial conditions. Okay, so but we still don't know what a squared plus b squared plus c squared are. So there's still more work to do. So you see, this is a very algebraic, type of problem with very little computation going on. And again, I'm kind of selling out by not showing you all the steps up here, and I didn't want to do that. I wouldn't get it right. I would leave out a term or make a mistake somewhere, So it's better off just to get it right and tell you the approach, the multinomial coefficient or the binomial the multinomial expansion or the binomial expansion works. I think the multinomial is slightly quicker, but then you have to know it, you know. All right. Now, so we need to figure out what a squared plus b squared plus c squared is equal to. Well, don't forget, a plus b plus c is equal to 0, okay? And so what we have right here is, oh, y'all, I should have squared this. Sorry. This piece is squared, okay? But you see, we know that this part is equal to 0, right? So we have 0 is equal to this, but we already know what this piece is right here. This piece is just, let me just write it down. And y'all notice, is equal to, well, I got this. Should that be a plus sign there? Oh, yeah, y'all, this is bad right here. This is a plus sign, sorry. This is plus, okay? Okay, so we have plus right here, okay? Now, notice that we know what AB plus AC plus BC is, right, from the beginning. It's equal to 7. And so what we get right here is 14, okay? But what this implies is that a squared plus b squared equals negative 14. See there, voila. So that helps a lot. That's negative 14, folks. So what do we end up with right here, folks? We end up with 95. Okay, now if we put minus 14 right here, this will be 95 times negative 7. So y'all, 7 times 90 is 630. Plus 35, and so you get minus 665 right here is our answer. Pretty cool, I think. Again, a lot of algebra, and the computations are relatively minimal. It's just there's algebra all over the place. Then you make substitutions as guided by the Vieta's results. Okay, so this is our answer. Equal to minus 665. Y'all, just thanks for sitting through that. If you're like me, you didn't. You just went to the end. I do that all the time. I just want to see the answer and then work it myself, you know. But notice that the problem, the natural approach is just to solve for A, B, and C and then substitute. But those of you who have much experience with these cubics, this has a discriminant that indicates there is one real number. Yes, these cubics have discriminants just like quadratics do. One real solution, and then, you know, two complex, the standard complex conjugate thing. Okay, two complex solutions. So it is something that's findable, but it's a lot of work even with a missing term to actually find that. And then you have to raise those things to the 5th power, which isn't too difficult for the complex numbers, and maybe not too bad really. But just, you know, just think of the time, you know, and again, your thoughts, maybe that's okay. But to try to find A, B, and C manually, I think is pretty challenging, you know. And then you got, again, you're not done even when you do that. Here, it didn't really get that dirty the way we did it here. We used well-known thing called Vieta's. This is why Vieta's works right here. And then the rest of it is just doing quite a bit of algebra bashing and then doing substitutions at the appropriate time. But anyway, that's it. And again, I don't know of a better way to do it. And it just gets harder and harder and harder. Like if this was a to the 7th plus b to the 7th plus c to the 7th or something. I think the algebra down here, maybe, I don't know, maybe it's just as manageable, but I think it's harder just from a human point of view. You can always verify these things using AI or something, or some kind of software, but it gets harder and harder and harder, I think, as the exponents gets larger and larger and larger. The algebra stays with you, but I still think there's a little more work just in terms of clutter, if you will. But anyway, that's the answer, folks. Thanks for viewing.